The polarization of an electromagnetic wave is a way of describing the direction of the electric field vector. In general, polarization is described as the shape traced out by the electric field vector tip. And that is evaluated from the point of view of a person that the wave is propagating towards. So if I'm standing here and the wave is propagating towards me, and I look at a slice of the wave perpendicular to the direction of propagation, like that, what shape does the electric field vector trace out on that plane? Whatever shape that is, that's the polarization. Polarization can be linear polarization. If you have a linearly polarized wave, then it has an electric field vector that traces out a straight line. It doesn't have to be directly along an axis like this. It could be along any direction perpendicular to the direction of propagation. It just has to be a completely straight line. Now, when we write the electric field, I might have an electric field that is, x hat times some amplitude times e to the minus j k z. Why, when I'm drawing these vectors, do they point in both directions? Because remember, here we're in phasor domain. So this electric field in the time domain, convention is to use a curly variable letter for that. That would be x hat e naught cosine of omega t minus kz. So as time, which appears inside this cosine, is varying, the sign of this amplitude factor E naught is going to flip from positive to negative to positive to negative, which is why this vector changes direction. Electromagnetic waves can also be circularly polarized. Which means if I am looking at the wave as it's propagating out of the screen towards me, the electric field vector, if I were to draw a plot of it, the tip of that vector traces out the shape of a circle as time increases. So it goes in a circle like that. We talk about the sense of polarization, particularly for circular polarization, meaning does the vector go around to the left or around to the right? So left-hand circular polarization goes around to the left, and right-hand circular polarization goes around to the right. Let me give you an example of that one. In the time domain, a circularly polarized wave is going to look like this. It's going to have one component that has cosine time dependence, and one component that has sine time dependence, like that. It's important to note here that the amplitudes of these two vector components are the same, and all their propagation information is also the same. They're at the same frequency, and they're going in the same direction. So if I draw a little xy plane here, remember x cross y points in the z direction, so z is pointing out of the board towards us, which is how it should be if we're evaluating the sense of a circular polarization. Let's take a look at what happens at time 0. At t equals 0, and let's assume that we are at z equals 0 also. At time 0, omega t is equal to 0, and cosine of 0 is 1. So we have 1 as the x component, and sine of 0 is 0, so we have 0 as the y component. So that's my omega t equals 0 vector. If I allow time to increase a little bit, and I say that what happens now if omega t is equal to pi over 4? Well, cosine of pi over 4 is 1 over root 2, and sine of pi over 4 is also 1 over root 2. So my new electric field vector is going to be pointing like this at a 45-degree angle. Omega t equals pi over 4. If I allow time to increase again to be pi over 2, omega t equals pi over 2, I get an electric field vector that is solely y-directed because cosine of pi over 2 is 0, and sine of pi over 2 is 1. So we're beginning to see here that the electric field vector traces out the shape of the circle and that it's going counterclockwise. It's going to the left, which means it is a left-hand circularly polarized wave, or you could say that it's counterclockwise. It is possible, and in fact it's pretty common, for an antenna to have a polarization that is not linear or circularly polarized. Linear and circular polarization are both special cases of elliptical polarization. That's what happens when you have anything that doesn't meet the requirements for linear or circular. So linear polarization, you have to have all the vector components, or not all, both, in phase exactly. So that means both cosine or both sine. They can have any amplitude you want, though. For circular, you need both vector components to have the same amplitude, and they need to be exactly 90 degrees out of phase. It doesn't matter if the x component is leading or the y component is leading or anything like that. That just changes the sense of the polarization, but the phase difference between the two has to be exactly 90 degrees. If one of these sets of requirements is not met, then the tip of the electric field vector will instead trace out an elliptical shape like this, where it will actually get longer and shorter, but it won't go all the way to 0. And it will still change direction a little bit, not like linear polarization where it never changes direction. So that is what elliptical polarization looks like. For antennas that are intended to be circularly polarized, there's a metric called axial ratio, or AR. It's often abbreviated as that. And the actual axial ratio is a measure of how circular your elliptically polarized thing is. So if you measure the length of the major axis of an ellipse and you compare it to the length of the minor axis of an ellipse, your axial ratio is then the major axis divided by the minor axis. This is usually reported in dB because everything is reported in dB in antenna world, which means that an axial ratio of 0 dB is circular polarization. It's always going to be, this ratio is always going to be at least 1, since we said that the major axis has to be on top. So any axial ratio value greater than 0 dB is a description of how not circular the axial ratio is. Why does this matter? Let's talk about polarization loss factor. The polarization loss factor which most books call polarization efficiency, but this one defines something else for polarization efficiency. I think it's silly, but we'll call that. The polarization loss factor is the square of the dot product of the polarization unit vectors of the transmit and receive antennas in your link. Obviously, these unit vectors should be in the same coordinate system. Usually it's in the coordinate system of the receiving antenna because that's where the reception actually occurs. This, if you work it out, is also equal to the cosine of the angle, the square of the cosine of the angle between the two polarization vectors. And you can use this to figure out what percentage of the incident power from the transmit antenna can actually be received by the receive antenna. Think about it this way. If I have an antenna with vertical polarization like this, these are my antenna terminals, I got a nice little dipole here, and then I have some incident wave with horizontal electric field polarization, I can't actually induce any current on this antenna. Current can't flow on this antenna because of this electric field, because there is literally nowhere for the current to go. The electric field vector has to be aligned with the dominant direction of current on the antenna. So let me write that down. The electric field vector has to line up with J on antenna. Otherwise, you can't induce currents and your antenna will not receive anything. And that's what this polarization loss factor is all about. In our next video, we'll put the whole thing together in the Friis transmission equation, because now you have enough information to calculate, if I transmit this much power from this antenna and I receive it with this other antenna this far away, how much power will I get?